So let's keep discussing the multiple linear regression model, which is a generic case compared with the simple linear ones. A typical multiple linear regression model, or with this example, can be written as the following. For instance, if we want to examine the relationship between the Pikachu's Thunderbolt power with its respect training time, diet quality, and battle experience, and we can build such a relationship with y representing Thunderbolt power, x1, x2, and x3 representing training time, data quality, and battle experience correspondingly. And we are going to use the explainer variable or explainer variables x1 to xp. In particular here, the p equal to 3 to explain the variation of the y or the dependent variable there. In particular, we have the following data with the first row representing the first observation with the training time at 1.5, data quality at 3, beta experience at 2, and Thunderbolt power is going to be observed as 42. Basically, we want to see whether as predictors, training, diet quality, beta experience can significantly increase our explanatory power for the variation of Thunderbolt power. And in total, we also have 10 observations. And here we assume they are having a multiple linear relationship model, or multiple linear relationship there inside the model, so that y can be explained by a linear combination of the predictors, which represent as S1, S2 until XP. Here we add the I as an index to tell you that we are going to have the different kind of y and x for different observation, while r ranging from 1 to n, with beta 0 representing again the intercept, and beta 1, beta 2, until beta p representing the slope for each of the term, and epsilon I representing the random error. Similarly to simple linear regression, the random error term, epsilon I, requires some common assumption. The first one is that they are going to have the mean 0, and the second one is common variance equal to sigma square, and third one, they should be RID. Last one, in order to draw a minimum experience inference, we need to assume epsilon I follows the normal distribution. There's a special representation for least square estimator. So we can rewrite the model as the following format. The reason for that is that we can take advantage about vector derivative to get the minimizer. So before we are talking about least square estimate for the beta 0 to beta p, and we are going to rewrite our model as the following format. Here we use the y1 to yn, which is organized as the vector of size n as represented as this bold case letter y, and we are going to represent the observation of x together with the intercept, common term for the intercept as y, x11 and x1p, and y and 1 and until y and p, and we are going to write the parameter that should be estimated. I'm going to call a theta, and they are the collection for the beta 0 to beta p, which has the p plus 1 term, and the epsilon as the vector of random error. And it can be shown that the least expression is just the same as that expression here. those two expressions are equivalent to each other. The least square estimator is a linear model that finding the vector, the theta hat, which minimize the y minus x theta square, or the L2 norm of the difference between the vector minus the x theta. Or put it another way, we are trying to minimize the y minus x theta transpose times y minus x theta. And this one is no different than the I from 1 to n's yi minus beta 0 minus beta 1 xi1 minus beta p xip and square of that. Those two equations are equivalent to each other. It's just that we are using the L2 norm to representing the collection of data more conveniently. So in order to get the minimizer for the beta 0 and on here beta p, as what we already presented previously, we are going to take the partial derivative about the following expression here, y minus x theta transpose y minus x theta with respect to beta 0 on here beta p 1 by 1 and set them to 0. That will give us a linear system of equation of p plus 1, so that we are going to find the solution about the first derivative and of them equal to be 0. This would be a very tedious work. Alternatively, we can utilize the vector derivative. In the vector derivative, we are going to dealing with the derivative with respect the vector rather than the each individual coefficient 1 by 1. In particular, if we have a function f of the vector x, assuming that x is q-dimensional, then the first derivative with respect to the vector can be representing as a vector of partial derivative of x1 until xq and order them as a vector. And the vector derivative of the linear combination of x transpose y or y transpose x can be written as the following: the partial x transpose y partial derivative of x. With some easy justification, you're going to find that this true partial derivative will give you the vector of the y if both x and y living in the space of q-dimensional vectors. And in the quadratic form, if we have A to be a symmetric matrix, and we are going to have the partial derivative of x transpose AX, take the partial derivative of x is equal to the following as 2 times AX. So in fact, this one can be easily justified by using the partial derivative of the first term x transpose AX and the partial derivative by x and taking the partial derivative of x transpose A and taking the partial derivative of the second term. And this one, just as what we have previously discussed, this one is just equal to the AX plus A transpose X, okay? So the first one is going to be using the first expression and second one using the second expression. And the following is going to be 2 times AX since A is the same as A transpose. With the this justification, we can apply in the chain rule to make the derivative with respect y minus x theta transpose y minus x theta. And we are going to first take the y minus x theta transpose with respect to y minus theta as a whole. And we are going to take the y minus x theta and divide by, take the partial derivative of theta. And we know that the first term is equivalent to C. We are going to take the first partial derivative of the first term here and the partial derivative of second term. That's the reason why we are going to have 2 times y minus x theta transpose. And the y minus x theta partial derivative with respect to theta, this is equivalent to C minus x. And so that we are going to have the chain rule, we are going to have the first derivative of the mean square loss or mean square error is going to be 2 times y minus x theta transpose minus x. Okay, so by setting them equal to 0, and we can get the minimizer of the mean square error there, and this minimizer would be our estimators or least square estimator. So in particular, we have x transpose x times theta equal to x transpose y. In order to solve out for theta, and we are going to times x transpose x minus 1 on the both hand side to the left of the matrix here and there. And this one will give us the solution for theta hat. They are just equal to x transpose x minus 1 x transpose y. And plotting back into our original model for the y equal to x theta. Okay, so this, remember, this is our original model, y equal to x theta plus epsilon. While the epsilon would be out of control, that's the reason x theta are the part we are trying to make the prediction, and y equal to x theta hat. And they are just equal to the x times x transpose x minus 1 x transpose y and times y. And if we are putting the x together with all those terms together, and if we denote it as H, and this matrix is called the hat matrix. And this hat matrix has very nice property that can be illustrated many useful property in the multiple linear regression model, which is out of scope of this class. But if you have any interest, you can talk about them and discuss them later in the more advanced linear regression course. And why is called hat matrix? As it's simple, if they timed onto the y originally, they basically give us our prediction or estimation for the y. That's why it's called the hat matrix. And the fitted value of y hat with the difference from the original y, the difference of them can be written as y minus y hat, while the y is no different as I times y, and y hat is hy, and we are kind of combining the two terms together, and we are going to have I minus h times y. And the h and the I minus h representing a projection of the data onto estimated space and error space. As you can see here, sometimes if we are representing or projecting the data into another space, sometimes that's equivalency, we are going to times in the left-hand side or sometimes in the right-hand side of matrix. That matrix is called a projection matrix. Basically, this hat matrix is going to project y onto the y hat, and this IH matrix is going to project the y onto the E. So basically, if your data is going to be living into the estimated space, then the data is the HY is going to project your original data into the estimated space, and I minus H is going to project the data into the error space. And a geometric representation could be written as the following. So while the Y is the data, and by times the Y with HY, and we are going to have X theta hat or HY. And this is equivalency that we are making the shadow onto the space of the estimated space. Okay, this round space is called the estimated space. So we are going to project Y to that space, and with the shadow representing the projection of Y or Y hat. And the difference of Y and Y hat, which is the blue line here, to representing the error space. Okay, so anything they are going to changing into this direction, the vertical one would be the epsilon hat space or the error space. Okay. Okay. So what's the red line representing? Red line representing the truth. Okay. As you can see here, the theta hat is not necessarily the true theta. So that's the reason why we are trying to using the X to estimate the Y. In the real case, this would be the epsilon and this line would be the X theta. And in the real life, the epsilon and X theta may well be different with the one we are provided as X theta hat and the epsilon hat. But since the blue line are just an approximation of the red line, and there's no way we are going to know the red ones. So the purpose about we are trying to make our estimation is make the blue one as close to the red one as possible. Okay. This would be the corresponding geometric interpretation. So basically, the estimation is saying that the estimated space is going to expand by the X because we can only explain the Y using X. And we are going to project the Y to the estimated space spanned by the X so that we are going to explain the model using only X, okay? And the difference between the estimated space and the observed Y are the space of the error space. So similarly as what we have for simple linear regression, it can be proved that an unbiased estimator for sigma squared is the SSE divided by n minus P minus Y. P representing how many predictor we are going to use. In particular, in our Pikachu example, the P is equal to 3. And we can test whether for each beta j, whether they are equal to a particular beta j star using a T statistics, which is going to follow a T degree freedom of n minus P minus 1. And we can use them to test whether the corresponding coefficients for x1 to xp are equal to 0 or not. Or better, we can test them when they are equal to the beta j star. And beta j star may not necessarily be 0, but if they are equal to 0, we can use this one to test whether they have a linear relationship between Sj and Y. Similarly, as what we have discussed for simple linear regression, we can rewrite the sum square of total and sum square of error together with sum square of regression. And so this calculation is a little bit tedious to record, but here's one important thing is G matrix is a vector of 1 times the x1 transpose. Basically, this matrix representing a matrix with all 1 as its element. okay? If we can use this one as a component, and we can actually write the SST, SSE, and SR correspondingly, and with corresponding degree of freedom will be written there. And it can be written that or proved that SST and SSE and SR are going to follow the T distribution individually with n-1, n-p-1, and p as corresponding degree of freedoms. Okay, the detail of the justification will be skipped, but if you have interest, you can try to prove yourself. And in the ANOVA approach for testing multiple linear regression, our null hypothesis would be there's no whatsoever relationship in our model. That means there's no relationship with respect to no matter x1, x2, or xp. So alternative hypothesis is that not all of them are equal to 0. In particular, in order to test this hypothesis, we are going to introduce the following test statistics as test statistic to test it, which is with SSR representing the sum square of regression of the model, and that is going to follow the T distribution with a degree of freedom P, and the SSE is going to follow T distribution with n-p-1. And so that the ratio about the two is going to follow a F distribution. And similarly, as simple linear regression, we are going to have MSR represent the mean square error of mean square regression model, and this one MSE to representing the mean square error, and F is no difference. F statistic is just MSR divided by MSE. Okay. Similar to simple linear regression, the larger the ratio is, the more significant the model can be explained by your regression model, okay? And we can also use the R square to describe the model fitting, which we already previously learned is 1 minus SSE divided by SST. And the larger the R square is, the better the model going to fit. Or we can also write it as SSR from SST, okay? And this ranging are ranging from 0 to the 1, okay? So to note that when p equal to 0, 1, 1, that means we only have one predictor to be considered in the model. And this is going to make the multiple linear regression a more general case, or simple linear regression as special case of a multiple linear regression. Okay, so in order to test whether model fitting is good or not, we are going to fit the model use the linear regression model. Similarly, as previous R code, we are going to use LM to run the model and multi-model representing the result. And we are going to use Thunderbolt power, regress onto training time, data quality, battle experience inside the picture data. And the summarization of data is going to be following. So as you can see here, the intercept equal to 34.78. And the training time is going to have the corresponding estimator equal to 5.58 and data quality equal to minus 3.903 and 0.1713. Okay, so theoretically, the model should be written as, so y hat, which is Thunderbolt power, equal to 34.7848 plus 5.5856 times with x1, which is the training time, plus minus 0.3903 times x2, which is data quality, plus 0.1713 times with x3. You'll note there the magnitude of the corresponding slope for x2 and x3 are very small compared with x1. So there's no coincidence because the t statistic for those two is going to generate a p-value has a value very large. As what we have previously learned that if the p-value is very large, that gave us strong evidence to reject the null hypothesis that, it's not going to give us a strong evidence to reject the null hypothesis of the beta 2 and beta 3 equal to 0. So that means we are not going to reject the null hypothesis of beta 2 equal to 0 and beta 3 equal to 0, while we can still reject the beta 1 equal to 0 and the alternative hypothesis of the beta 0 equal to 0. Okay, so basically this would be the one-by-one individual term with the corresponding hypothesis testing for each individual term. That means from the model fitting, it implies that only the training time can significantly explain the data variation of the model. But again, the multiple linear regression model has a very high value equal to 0.9944. So with corresponding F statistic can be calculated as 35.8.3. They should follow the algorithm equal to P and n minus P minus 1, which is 6, and with corresponding P value equal to 3.73 times 10 to the power of minus 7. So compare with the previous result, if you still remember, previously, when we have only simple linear regression, we are having P value equal to 0.9933. That's why we shouldn't simply rely on the R-square to judge whether the model is good or not, because even the down inequality and the battle experience does not explain a lot from the data. Actually, we do not have significant evidence to claim they're important. We still get the multiple linear regression, the corresponding R-square increased from 0.9933 to 0.9944. Although you do notice that the increment about the R-square may not be that large. That's reflect the point that we have previously discussed. We shouldn't rely on the R-square to representing the model fitting. Rather, in some practical point of view, we are prefer to use adjusted R-square. So if you compare with adjusted R-square 0.9917 with the previous adjusted R-square 0.9925, as you can see here, if you only use adjusted R-square, and we are going to think this model is better than 0.9917. Okay, so that means if we are comparing an adjusted R-square, we may prefer the simple one compared with multiple one, because the adjusted R-square is going to be adjusted with respect to the model complexity. So that's the reason why sometimes we prefer to use the adjusted R-square rather than the R-square to judge the model is good or not. But similar to the multiple R-square, is the larger means the better fitting. When we talk about the adjusted R-square, we prefer to choose the model who have the larger R-square if the data is fixed. Okay, so this would be the generic ANOVA table, and here we have the model variation that can be explained by environment by the model at 690, and the residual sum square at 3.85, with the mean square regression at 230, with residual sum square equal to 0.64, with corresponding F statistic calculated as 358, and corresponding PD value as 3.73 times 10 to the power of minus 7, which is extremely a small number. That means our model can be explained the similar proportion compared with unexplained part. And this will be the code for generating a ANOVA table. And similarly, as what we have discussed for simple linear regression, we also need to make the diagnostic. Basically, whether we can assume the common variance assumption or whether they have some independent identical of the distribution of data, and whether the data can be assumed to be normally distributed. As you can see here, those two plots are very similar to the previous diagnostic plot for simple linear one. In particular, there's no systematic change about the residual with respect to the fitted value. And also, the variance are commonly observed around positive 1 to 1, negative 1. And most of data is going to follow a straight line with a little bit exception in the third observation, but it can be explained by we do not have that much like observations. So basically it means this model have no significant violation about those three important assumptions, which is RID assumption about random error, common variance assumption, and normality assumption. Okay, that would be all for multiple linear regression model. And I hope you have learned the simple and multiple linear regression from this class. Thank you.